story, and thank you for asking me. Although in the guest house with patchy internet, and one day notice it's a reinforcement learning exercise. We'll learn today whether it works or it doesn't work. So my history is that I used to work. So I'm probably one of the very few people who would say that they don't do reinforcement learning. I mean, Professor Borka started by saying that I'm a control theory person, so I'm going to start by and large by saying that I'm not a reinforcement learning person. But I did a fair bit of planning in my thesis, as well as advised a couple of students at University of Washington, co-advised by Dan Weld. And most of the work that I will be presenting today is work by Andrei Kolobov, who is now at Microsoft Research. And this work is dated a little bit. Most of this work finished by 2012, towards the end of 2012. So it's a couple of years old, but I think it's still very relevant, and there's still fascinating things to extend. Now, I want it to be as interactive as it can, so please ask me questions, and we'll. Let me start by citing Rich Sutton's talk today, and he laid out what he thinks everything is reinforcement learning, and AI is reinforcement learning, and I subscribe to that view as well at some level. And said that you can be doing control, you can be doing prediction. So I'm not doing any prediction. Absolutely everything is known to you in advance. I just need to be smart enough to be able to compute what I need to compute. And it will be full sequential. And obviously, because I know everything, I know the model, and therefore you don't need to learn model or to do anything model free. And we will stick to values. Mostly we will keep switching between tabular and function approximation representations a little bit in the talk. And there is a lot of work in planning which does Monte Carlo in addition to TD style, like Bellman updates. I won't talk much about the Monte Carlo stuff, but there is a lot of work in there. So I would begin by trying to place this talk in the context of what we have been seeing up until now. So as I said, that this is not reinforcement learning in the sense that there is no learning, and that is relatively clear. And usually when reinforcement learning folks use the word planning, that is exactly what they mean, that the model is known. But when the planning people actually think of planning, they most often than not add one additional dimension, which is that not only do I know the model, I know the model in usually some sophisticated representation, some high representation. So the model of the world has been declared to me in some representation. It's usually symbolic and usually factored, and that allows me to model, to represent really large problems in a really small amount of space. That means that the kinds of problems that typically we are interested in are huge. So yesterday Shiva was talking about 1,000 states and 10 actions, and for policy iteration that is definitely large. But the kinds of problems we'll be talking about sometimes can get into 2 to the power 800 states. And we would not even bother proving any bounds, so there will be no theory in terms of bound proving. We'll just try to solve it. We'll just try to empirically see what actions we get and can we get better and better, and that's sort of going to be most of the exercise. Now, just by historical accidents, planning community, all the way connected with the classical planning world, the AI world, it has stayed more goal directed as opposed to rewards. So up until now we have been talking about infinite horizon, discounted rewards, and those are great settings. But most of the talk today is not going to be talking about rewards. In fact, I am going to prove that the model that we are going to talk about is going to be strictly stronger theoretically, and in practice, if you have the knowledge of goals, it allows you to do some different kinds of heuristics and so on and so forth. Now, one other, again, historical accident that happens is because of the connections with the search community, we will never be solving for the whole state space. Obviously, 2 to the power 800 states, you don't want to be solving for the whole state space. So what you would be doing is that you would be given a start state. And given the start state, you would want to take the best action possible. UCT does some of that as well, and therefore UCT has also now been a legitimate planning algorithm, even though it doesn't assume the model. And heuristics come from the model. That's a different line of literature that I'm not getting into. So we would be given the start state, and we can just get rid of many states because they're not relevant in the specific planning problem that I want to solve, which is given the start state, I want to get to the goal. And last but not the least, we would love it if we don't give anything else other than the domain description to the algorithm. So oftentimes we say, yeah, we should use function approximation, and yes, a value function is a sum of basis functions, and yeah, your basis functions will be given to us by the domain designer. Not going to happen. Not going to fly in planning community. Essentially, no basis functions are known. You are given the state space in the representation, you are given the actions in the representation, now do the best you can. Okay? So this is sort of the delta from what we have been doing in the last 3 days. Model is known, so it's an easier problem. Model is usually not flat, it's represented in some symbolic representation, allows very different techniques. Usually goal directed, seems similar or weaker, actually is stronger, we'll talk about why. Knowledge of the start state and no additional domain input other than the domain description. So far so good? Now in this talk, I will try to send out these 3 messages or 4. First of all, you don't need exploration. There's no exploration. It's all exploitation, right? So you know it's a purely computational problem, and also one other delta, VI does not mean variational inequalities anymore. Let's come back to reinforcement learning. VI simply means value iteration. Thank you. You don't need to do Q-learning. You can solve VI or some version thereof. It's a purely computational problem. So these are the 3 messages that I'd like to get across. Sometimes you can ignore states. Some states are not important. If you can figure out which states to ignore, that reduces your search space. That's a good thing to have in your algorithm. The representation is crucial. If you have an interesting representation, there are interesting properties of that representation that you can exploit. Okay? It leads itself to expose interesting structure of the problems. If I give you a flat representation, a flat MDP, there is very little structure in there exposed in the representation. You can do some analysis, you can run some very complicated algorithms to discover structure, that's great. But if you have an interesting representation, some of that structure is relatively free or less cost. Okay? And last message is that in goal-directed MDPs, if you know that you have a goal, that allows you to use that knowledge in making better algorithms. So not too complicated messages. Some states can be ignored. Search is good. Representation is good. Goals are good. Basically trying to use the structure of the problem and making efficient computation. Very AI-minded worldview. All right? So let's begin. This is going to be my agenda. Yes, question.
So, a couple of short comments. One is, so this work on things like first order MDPs, where people make the claim that there's no function approximation problem. In other words, you just unroll it, use the value iteration, and what you get is the right solution. There's no notion of having to do function approximation, which is, to people in RL seems a little strange, but
I would not even agree to that.
Okay.
So even in first order MDPs, what you do is that you want to construct the basis functions automatically and then do function approximation. In fact, you are living in a world where there can be unbounded number of objects and the problems can be of as large a size as possible. In order to solve such problems, which are represented in first order language, you want to expose generic first order structure that may be applicable to a diverse set of problems and then learn values for it. So I don't actually agree that first order MDPs don't lend itself to function approximation. In fact, they do. Moreover, some of the time we will be talking about function approximation. The only difference would be that the basis functions would not be given by the domain designer. We would use the representation to discover the basis functions.
I see. Yeah, the second question I had was on infinite domains, but you already mentioned that, so yeah. Okay.
Good. So now I expect that many of you, okay, so here's a quick survey. How many of you have heard of LAO star? Right, 4 people, good. How many of you have heard of RTDP? Better. But how many of you have heard of labeled RTDB? Much less. So clearly this kind of literature has it's like a continuum, right? There's control theory, there's operations research, there's reinforcement learning, there's planning, and depends on which communities talk to which community. So some of this literature is new, so I'm not assuming anything. And so the first half of today's lecture is going to be some kind of a background, sort of like a mini tutorial. I'm not going to cover all the techniques that are there in the planning literature, but some of the ones that are, I think, interesting, that make some of the points that I'm trying to make, and also will be relevant to the stuff that I'll talk about, which is Andre's work. And then in the second half of the talk, we'll talk about some algorithms and some models. So this is going to be the agenda. And so especially in the first part of the talk, when we're doing background, I would really invite questions, because I want you to take home some of these very basic algorithms that I'm going to be talking about today. Okay. Why? Okay. Now, let's begin with infinite horizon discounted reward MDP, the kinds of MDPs that we have been seeing up until now. We have a set of states, we have a set of actions, we have a transition model, we have a reward model, and we have a discount factor, right? Now, it's not necessarily a foolproof argument, but, it is not clear where the gamma comes from. Sometimes it may be suggested by the inflation rate or the interest rate and so on and so forth. But usually we just assume, yeah, we'll put some gamma, 0.99, 0.95, it's all right, it works out. We need this gamma to be less than 1 because we want our value functions to be bounded. Is this a good value function representation? We don't know. We also know that the value of gamma can actually affect the policy. The optimal policy can change significantly, and it's not clear whether we are doing the right thing. So now sometimes this is a good model, no question about it. But sometimes there is no natural notion of gamma, and we are just artificially imposing gamma on top of it. So the first thing that we want to do is to get rid of gamma. Now I know it's going to scare a couple of you. Many of you may have seen undiscounted problems. So from infinite horizon discounted reward MDP, I'm actually going to take you towards a model that we call stochastic shortest paths. Okay? And in your mind, just think of shortest path. Think Dijkstra's algorithm. Think shortest path. I want to go from one goal to one state to another state, just a graph, standard thing, except that now I have stochasticity in the domain, the kind of stochasticity that MDPs usually have. So I want to go from infinite horizon discounted reward MDP to what we call stochastic shortest path MDP. The first thing that needs to go is the discount factor, right? So discount factor goes, of course, it's just the second thing that goes, unfortunately. So in stochastic shortest path, because we are going short, right? We're not optimizing for reward, we are minimizing for cost, more or less. That's what shortest path problems are. We are first going to convert reward to cost. That's not a big deal. It's standard. You can think of C is equal to minus R. Then we get rid of the discount factor, and moreover, because now we want to get to a goal, we are going to explicitly introduce a set of goals. Okay? And this is exactly the model. So it's a very similar model to infinite horizon discounted reward. We have a set of states, a set of actions, a transition function, the cost for taking an action, and we want to reach a set of goals, or any one of the set of the goals. And now what do we want to optimize? Well, we have been maximizing expected reward over infinite time, expected discounted reward over infinite time. Well, we have to change that a little bit. So we are first going to minimize. We are going to minimize cost, of course, expected cost. But cost to do what? Well, cost to reach a goal. So therefore, the model says you start acting, you go on, and once you reach the goal, you stop. Okay? So there's an explicit absorbing state. As soon as I reach the goal, I am done, my process finishes. All right? Full observability is the MDP assumption. But if you think about the horizon, it's not technically infinite horizon, and it's not technically finite horizon. Because finite horizon usually assumes that you know the horizon, it's bounded. And infinite horizon says you're going to go on forever. It's somewhere in the middle, in this fuzzy region, and I'm just going to call it indefinite horizon. That is, I can take unbounded number of steps, but once I reach the goal, I finish. Okay, so that's the notion of indefinite horizon. As long as the problem is well formed, as long as the value function is well formed, we are still in good territory. Okay, so Bellman equations. The Bellman equations are pretty much standard. You don't have a discount factor, which you usually will have somewhere here. And instead of max, you have a min. Instead of reward, you have cost. And then you add a base case, which is that the value of a state to reach the goal, starting from the goal is 0, right? So it's exactly Bellman equations. The dynamic programming will have slightly different properties, but it's exactly the same kind of dynamic programming, value iteration, policy iteration that we're talking about. We just add a base case for state which is a goal, it's 0, and for every other state, it's a standard minimization of this Q value, and the Q value will be, you are using costs instead of rewards and no discounting. Okay. So what do you think? Well, I've probably already given the answer. But if you think about rewards, and if you think about cost to reach a specific goal, which one feels more general? Costs feels more general? Well, costs and rewards are equivalent. But in infinite horizon discounted reward, there is no goal. You don't need it. You can just get any random reward and you just can keep going. Whereas in stochastic shortest path, you are trying to reach a goal. So which feels more general? Often people say that goals is less general and reward is much more general, because reward you can put a lot of reward on the goal and no reward elsewhere, or you can decide to give some state some reward, some state some reward, and so on and so forth. Actually, they are equivalent modulo the discount factor, and once you start to add the discount factor, you realize that stochastic shortest path is by definition a more general model. Theoretically, I'm not saying that the algorithms will have the same performance, but theoretically, discounted reward MDPs are actually a special case of stochastic shortest path. And let's just prove it, because the proof by Bertsekas and Sitsiklis is one slide, half a slide. It's not even a proof, it's just a construction. So the construction goes as follows. This is my original reward MDP with a discount factor. Suppose I am in a state, I can take an action A and I can go to state S1 with probability T1 and my reward is R1, and state S2 with probability T2, my reward is R2. Right? So you can write the value equation. Value would be, Q value for example would be R1 plus T1 times V of S1, gamma V of S1, and plus R2, or T2 times R2 plus gamma times V of S2, right? Now equivalently you can convert it into a stochastic shortest path problem, where you explicitly define, first of all you convert rewards to costs, that's very easy, max min, so you convert cost to minus R1, minus R2. But you define a goal state, remember stochastic shortest path needs a goal, so you define a goal state, and then you say every state can transition to this goal state. Okay, so you add edges from basically every action and to the goal state, right? And the transition happens with probability 1 minus gamma. So with a very tiny probability, you transition to the goal state. Actually, technically, this is coming from the outcome of A, so it should be coming from here. So now if you try to compute the value of reaching the goal, right, the Q value, Q of S0 comma A, and the transition probabilities you have to also multiply with gamma, because you want the sum to be 1, right. So then this becomes minus R1 plus gamma T1 times V of S1 minus R2 plus gamma T2 times V of S2, which is exactly what we had here, except the minimization was maximization. So actually you can reduce any discounted reward MDP into a stochastic shortest path. Is it a good thing to do? Should we do it? I'm not saying that for algorithms, but from a theoretical understanding, we know that it's a special case. Okay, and one last bit of theoretical jargon. When would value function for a state in an SSP be well formed or well defined? Now, in infinite horizon case, we use the discount factor to make sure that the infinite sum is bounded. We are not doing discounting. That means there is a danger that the infinite sum may not be bounded. And we have to actively avoid that danger, right? And to avoid that danger, we will, the original stochastic shortest path model, as Bertsekas defined it, use the following two conditions. For now, we will not worry about these conditions. We'll come back to them towards the very end of the talk. So A, there is a proper policy. That means from every state, I can reach the goal with probability 1. Okay? Because if this doesn't happen, if I can't reach a goal, suppose I can only reach the goal with probability 0.7. Whatever is my expected cost for 0.7 is fine, but what happens to 0.3? It gets multiplied with infinity, because I'm just going on, and if my costs are becoming unbounded, then I'm just going on. So you need a proper policy to reach the goal with probability 1. Give me a sec. And then second condition is that it is possible that you have an improper policy whose value is even less. You don't want that. You want that value to be, or the cost to be infinite, because you want to get rid of these bad improper policies when you are doing computation. So you add another constraint that every improper policy should incur a cost of infinity for every state from which it does not reach the goal with probability 1. And under these two conditions, actually, your standard value iteration algorithm, your standard policy iteration algorithm, standard Bellman update equations, all of these things just flow very, very sweetly as they do in the infinite horizon discounted reward set. Chaba.
Yeah, I was just wondering about whether the first condition is really necessary for making sense of things.
It's not. And we will talk about extensions of SSP models exactly towards the end of the thing, where we will we'll try to relax as many of these assumptions we can. And that is actually very interesting piece of current research that has happened. Believe it or not, this research happened in the last 2 years or 3 years. So, yes.
What about the average reward setting?
I don't know much about average reward setting, but it's a great setting, and I think at some point I should really read more about it and see what works and what doesn't work. Chaba might be able to answer more on those questions.
So one of the standard problems is called pole balancing, where you try to balance a pole like on your hand or on a cart for as long as you can, so you do want to avoid falling over. And it doesn't seem like a shortest path problem. And also the termination is not a goal, it's something you're trying to avoid.
Right. So again, let me reiterate. Theoretically, you can take that problem and convert it into stochastic shortest path. It's a very valid stochastic shortest path. The goal will be a sort of an artificial state, and if you solve for that optimally, you will get exactly the same policy that you're looking for in your discounted version. That said, the algorithms for stochastic shortest path, which explicitly make use of the goal, may not really be as efficient and as effective in that setting. So I'll try to separate these two things. Theoretically, you can take that problem, define an artificial goal state, have every state transition to the goal state with probability 1 minus gamma from every action, and that model will be exactly equivalent to the original infinite horizon discounted reward version of the pole balancing problem.
That may be so, but it seems crazy to call it a shortest path problem because the paths are going to be negative. And it seems crazy to call it a goal task because the only termination is something you're trying to avoid.
Exactly. So I am not asking you to solve it that way. I'm saying that you can convert it. Mathematically, it works. So algorithmically, when you have goals, the knowledge of goals helps you to get efficient algorithms. And when you don't have goals, then there are different algorithms which are more effective. Right.
So maybe what Rich is trying to say is that if the costs are all negative, then it's kind of like really strange to call this shortest path problem, right?
Right. So if costs are all negative, then you have to start thinking about, well, yeah, exactly. So I agree, but yeah. Okay.
Question?
Yes. Most stochastic shortest paths that I have seen have worked on finite graphs, but I don't remember if that was an assumption. I have to check theoretically. Okay. All right, Shiva, yeah.
So if I've understood correct, when you say every, what do you call it, like normal definition of an MDP can be reduced to a stochastic shortest path, you mean that by your definition of MDP of I don't know what you want to call the regular thing, infinite discounted, okay?
Yeah.
And stochastic shortest path on the other hand, given an instance of this, you can define an instance of this
solving which?
Which are equivalent. The
Like-
policy is the same. The optimal policy is exactly the same.
But it cannot go the other way around. Are there stochastic shortest
Yes.
path problems
Yes.
which cannot be
That is
solved
correct.
by solving an
This
infinite
is an
discounted
accurate
cost?
figure. So yes, there are stochastic shortest path problems which cannot be converted into discounted reward, basically because they are doing undiscounting, and so the effective discounting distance is not there. It's an indefinite horizon problem.
I know there's an infinity, but can you not cope with that by doing like a Rmax or?
You may be able to
some kind of-
approximate, but this is a
No, not
theoretical.
approximate. I'm
No,
saying.
so, yeah.
Okay.
Formally, I think this is exactly accurate.
Okay.
Okay.
So I have one more.
Yes,
Sorry.
Rich.
So also in reinforcement learning in their MDPs, they have a standard formulation called the episodic case, where you have terminal states. And I think what you're really saying is that you can always convert any continuing discounted case to an episodic case.
Yes.
And it may not be.
Undiscounted episodic case. Yes,
Yeah.
exactly. I think undiscounted episodic case might be exactly the stochastic shortest path. Or we have to check. Okay, because these two conditions may be checked. All right, so let's now move to the algorithmic side of things. Now, the next thing I'm going to do, so this is just modeling. This discussion will become very handy here in the last part, but now these two things integrate rather well. And so the next thing I'm going to do is that I am going to start by talking about limitations of VI and say that how heuristic search can help. So obvious limitation of VI, enumeration of state space, curse of dimensionality. We all know this. We have been people have been working on this for 30 years. Now, one particular insight that a lot of reinforcement learning people do not really work too much on, although UCT is now trying to bring it by sampling, is the idea of heuristic search. So now go back to your AI 101, pretty much the first week of that class. You all have learned A-star algorithm. And what we are going to do, so think of A-star as regular graph. So it's a A-star heuristic search on regular graphs. What we will do next is that we will generalize A-star to these kinds of MDPs, which are equivalently in graph theoretic terms called cyclic and/or graphs. So again, the exact nomenclature is not important, but the point is there are loops, there is stochasticity, and so I'm going to try to generalize A-star to the LAO star algorithm, which, believe it or not, came from UMass, right? Shlomo Zilberstein's group, and Eric Hansen was the student. So the main two ideas that we will add is that A, the start state is given to us, so we can save on computation. So in some sense, going from all sources shortest path, we are going to single source shortest path. And then usually we do this by assuming that we have some kind of a heuristic function, right? You all know what a heuristic function is in the context of A-star. Have you heard the term admissible heuristic functions? Does someone remember what an admissible heuristic function is? Yes. Always underestimates. That is exactly the wrong answer. And you may have seen it every time that a heuristic function always underestimates. That's actually not true. Because if I'm maximizing, the heuristic function always overestimates. So you should always think of the heuristic function as the optimism, the optimistic value function, not in the face of uncertainty, but in the face of certainty. So it's the optimistic value function for the value that I'm trying to compute. Now, if I'm trying to minimize, my optimism says, yes, I am at the goal already, right? My value function is 0. 0 is the most uninformative admissible heuristic function if my all costs are positive. And similarly, if I am maximizing, then my optimism is that I can get infinite reward or really, really large reward. Okay? So we are going to use a heuristic function that somebody gives us. And where does that come from? Again, planning community uses the representation to compute these. Okay, so now we have to extend SSPs to add the idea of start state. So let's just add start state, okay? So we add start state and that's it. So this is the model that we are going to solve. We have set of states, actions, transition costs, goals, and a start state under these two conditions. Okay. Now, first question. What is the solution that we are looking for? So in a regular MDP, we are looking for a policy. In an MDP with a static state, what are we looking for? Do we need the full policy? This is the time where you nod your heads. one of the three ways. So let me repeat the question. So you, in a regular MDP, you want a policy which is a mapping from states to actions. It's a complete mapping, so I know exactly which action to do in exactly each state possible. In an MDP where a start state is given to me, am I looking for the whole MDP policy? What am I looking for? Does this policy have to be defined at least for S0? Yes, exactly, right? Now, suppose from S0, I go to S1 by following this policy. Should it be defined from S1? But from S0, suppose I never go to S2 by following this policy. Do I need it to be defined for S2? No, exactly. So let's formalize that idea. We want a partial policy. Partial policies are mapping from states to actions where state is a subset of states, S prime to actions. But it has to have a property. And the property is that it should be closed with respect to itself, assuming that we are starting from any one of the start states, right? So it's a partial policy, but it should be defined for all states S prime that are reachable by itself, that are reachable by S starting from the start state, okay? So let's do a quick example. Suppose I tell you that from S0 you can do A1, left is A1, right is A2. From S1 you can do A2, from S2 you can do A1. Is it a partial policy closed with respect to S0? Let me draw this in red. Is this policy closed with respect to S0? See, if I take this action from this particular S2, with some probability I am going to get to S6, and I haven't defined what can I do in S6. So therefore, this is not the policy that we are looking for. But maybe if I add A1 and I add this edge, now is it a partial policy closed with respect to S0? It's defined for all the states that it is going to visit, right? And so now the answer is yes. So notice that the solution is a much smaller part of the graph that we are looking for, defined on a smaller number of states, which may suggest that maybe we may not even need to visit many states if we can prove that they are suboptimal. Question?
So does this not assume that some kind of block diagonal kind of transition matrix? It's eventually doing that, right? Not block diagonal, so you restrict your matrix to S1, S2, so these are the only things that are talking to each other. So you are essentially assuming that there are other transitions are zero, right? I mean, so
no.
What does it have to do with the stochastic shortest path? I mean, it's a statement on the transition matrix, right? I mean,
not on the transition matrix, because on the other hand, from S2 I may have decided to take action A2,
okay.
in which case I may want it to be defined for the state and so on and so forth. So all the action that I am taking in each state are in my control.
Correct, but no, my question is, because of stochasticity, you are not going to be thrown from S2 to S8. Right?
That's right.
So you are saying P of S2 under any action to S2, S8 under any action is 0.
But it is 0, we know this already. MDP
So-
is given to us.
Okay, so this, okay, so it's essentially a restriction on the P, right? No.
You can think of it as a restriction on the P, but really the transition function is given to us. And more often than not, in the planning settings, we assume that one state with one action doesn't really go to all the states at once. I think that's the question you are trying to kind of ask. Yes, if I am picking a block from this table, with very high probability it's in my hand, with some probability it's on the table, with some probability it has fallen down, but suddenly it has not jumped and sitting on the clock there. So that sort of assumption is always there. Yes, Rich?
But it's possible that many states could be next. You may pick up a block and someone else may walk into the room.
Yes.
Or you know.
Yes. And so, exactly. So you may have many transition states, and so the construct says that the policy graph, the partial policy graph, should be closed with respect to itself. If by closure we mean we have to really visit all the states, then you can't help it. Exactly. Okay. Then I will define this idea of greedy policy, where you are just taking, given a value function, you can just take the argmin and you can convert it into a policy. And you can also define the notion of greedy partial policy rooted at S0, where you start with a value function and then you define the best action at S0, and then you go to the various states that it visits, define the best action for those states using the current value function, and repeat it until there are no other states that you can visit, right? And that you can call it the greedy policy graph if you're looking at it in graph theoretic terms. Okay. The second thing that we are given is the heuristic function, as we have discussed. In this case, a heuristic function is going to estimate V star. It's sort of going to give us an indication about how good my state is, and usually it is used as the initialization, but it can also help us avoid seemingly bad states. And an admissible heuristic function would be optimistic, which in this case would be an underestimate of the value function because we are minimizing. All right. So now we are ready. We have defined our model. We have defined the output, and we have defined the heuristic function that we are going to use in the computation. Now we are ready to learn the first, or in this case, I'm going to define a general formula for heuristic search for MDPs, a very general rubric of algorithms, and then instantiate it in two different settings. One is LAO star, one is labeled RTDP. Now think about VI, think about prioritized VI. What is the intuition? Residual in some state is very high, I should go back it up, right? That's a standard intuition. We all have done it. When some value changes, then we change the values of its predecessors and stuff like that. Moreover, now we are doing two multi-objective things. We are trying to find that subset of states, which is the right subset of states to look at, and then trying to do Bellman computations or value iteration like computations on that subset. So the states where the residual is high is very important, but the states that are no longer even reached in the greedy policy are also important because you don't need to worry about computation on those. So you really have to come up with this sort of an alternating scheme where you're doing some search, figuring out which subset of states I should be looking at, and then doing dynamic programming and computing the right value, and then figuring out which subset of states I should be looking at, and just going back and forth on it, right? So that's the intuition. And the general method is called find and revise, where you essentially find a state that satisfies two of these properties, that A, it's in the greedy policy graph, and B, its residual is greater than epsilon, and then you perform a Bellman backup on it. And as long as you keep doing it until no such state remains, you are guaranteed convergence for this particular model. Okay? So this is really a really simple algorithm if you think about it. I'm looking for this one state which has high residual, and it's in the greedy policy graph rooted at S0 based on my current value function. If I did not find such a state, then I am done, I have converged. But if I found such a state, then I find such a state and then I do a Bellman backup on it and repeat. So this thing is the find and this thing is the revise, which is a DP update. That's it. So now we are going to instantiate it. And convergence is guaranteed under the following conditions: that the heuristic function is admissible. Actually, in that case, it's guaranteed to optimal, and no state gets starved in infinite find steps. So you don't just starve of one state; its value never gets updated. You don't want to do that. You want to make sure that every state which has such a property gets gets picked, and that's it. So as long as these conditions are met, then the convergence to V star is guaranteed. So let's look at one algorithm. The algorithm is called LAO star. Okay. Again, think A star in your mind. Usually in A star we have a set, a fringe, and in that fringe we are figuring out which state to expand. We are going to go with exactly that intuition. So we'll initialize with S0 in the fringe, and we'll repeat the following steps. We will expand one or more, so this is also a family, so we'll expand one or more states on the fringe. Okay? We'll expand it. As long as they are in the greedy graph, that means that new states may be visited. You have to initialize them, so you will initialize them with the heuristic value. Then you will pick some subset of states that is relevant, and you will do some computation on it, like some Bellman backups, like some value iteration, maybe to convergence, maybe not to convergence. We'll think about it. And then we will recompute the greedy graph. So this is one example of this alternating thing. And we'll keep doing it until the greedy graph has no fringe and residuals in the greedy graph are less than epsilon, the standard value iteration convergence condition. Okay, so if this is too much, then we'll just do an example very soon. Yes, Rich.
So one of the key steps here is you're computing sort of the costs so far in the greedy
That's right.
graph. So that's just part of computing the greedy graph, is you're also computing the cost so far at all the fringe nodes?
So when you do revise computation, that's where you are doing Bellman update and so on and so forth. And after you have done some Bellman updates, you look for the greedy action so far in the value function, and that changes your greedy policy graph.
So normally in the Bellman computations, you don't have a cost so far. You have a cost to go.
Oh, so no, you are not computing cost so far. You're only computing cost to go. But since you are starting from a start state, you are looking for, yeah, but no, we are not doing costs to go. Why should?
You're doing costs so far.
We are not doing cost so far, yes. How does that affect? We are only doing cost to go.
But you take into account the actual cost in the graph, right?
That's
While
right.
You're doing the cost to go.
Yes, exactly.
That's the cost so far.
Well,
What?
It's a standard V of S as we do it in infinite horizon discounted reward. We essentially say what's the long-term expected discounted reward starting in this state. So the value is exactly the same. It's what is the expected cost to reach the goal starting in this state. So we are only looking at future, not looking at the past.
You have to, inside the greedy graph, you have to maintain what's the cost so far from the start state.
We are not doing that. So that's the change from the A star algorithm. So in A star algorithm, you usually have f is equal to g plus h. And I think you are looking for the g function. Where is the g function? There is no g function. So exactly. So because we are doing value iteration so I'll instantiate it with what I mean with some revised computations, but you can think value iteration in your mind. You can do all the value iterations until convergence. So really, if you have passed so many messages, then the cost so far is no longer necessary. That is necessary when you are doing an incremental algorithm like A star, where there's only one computation step at each point. Okay, keep thinking about it. But the algorithm is sound. You don't need to compute cost so far, which is the g function. Okay, and so the family makes sense because we haven't defined how to find the states, we haven't defined how to choose the subset, and we haven't defined how many or what revised computations to do. So let's do it in one specific case. So this is the original LEO star algorithm that came in '98, and basically you do very similar to A star. You pick the best state on the fringe, best defined from maybe heuristic function, and you take all the states in the expanded graph that are relevant for this change now, and then you compute VI on this subset. So let's do this. So this is my original graph that I am trying to do computation over. Initially in my fringe I will have S0. Okay, so this is my fringe. So right now my states that can reach S is only S0. The S0 can reach itself, and that's it. So I do value iteration. Now what does it mean to do value iteration just on this state? Well, basically you are updating the H values and you are sending them back and doing one Bellman backup. That's about it. So you do that, and that allows you to figure out what's my greedy action so far with this knowledge. So now my greedy action, let us suppose, is A2. So this becomes my greedy policy graph. Now I repeat the process. So now I figure out which states go in the fringe. Well, these states go in the fringe. I expand one of them. Let's say I expand this. I figure out which, I initialize them. I figure out what's the new set of states I should do computation over, whose values could have changed. That is that. I do value iteration. So now my value of S0 has changed, value of S3 has changed, and then I recompute the greedy graph. And maybe now it's this greedy graph, because maybe it realizes that A2 is a bad action based on this new knowledge. Maybe A1 is a better action. Again, I find the fringe, expand, initialize. Maybe one of them is a goal. I keep repeating these until I get this to this point. So now I am doing value iteration here, and at some point I realize that this is the state in the fringe. Okay, so I expand it, I find these, and then I do value iteration, and now I have converged, because there is no other state to be added because my greedy policy graph hasn't changed. Once this happens, you can output this greedy policy graph as your final policy. Now notice a couple of things. First of all, S4 was never expanded. I never needed to. I could really prove that, look, based on my heuristic value, I know that I don't need to expand it because my heuristic value is admissible. So I can already prove that S4 will never be reached from S0 by following the optimal policy. And moreover, S8 was not even touched at any point. And that's the power of heuristic search algorithms, that some states can be absolutely ignored for efficient computation. Okay. There are some refinements to LEO star algorithm. For example, if you think about it, I'm doing one expansion and lot of computation. So I'm doing one expansion and then doing lots of VI. And then I'm doing one expansion and then doing lots of VI. That's really, really slow, right? Because in A star it works because my incremental computation is very small. But in LEO star, that's not going to work. It's just too much computation. So what people did is that they changed this. So first the reaction was, don't do complete VI, do VI until your greedy graph has changed, right? Because as soon as greedy graph changes, these states are no longer relevant. Let's just recompute the greedy graph. The second change was, don't expand just one state, expand all states. And the final change was, don't even do too much of VI, just do one backup per state or something like that. And in fact, all these changes were done essentially for empirical reasons, and they found that this particular algorithm really ended up being extremely fast. There was a particular backup order that they used. And the beauty is that you can keep defining these. You can change your find step, you can change the amount of computation you do, because the find and revise tells us that as long as you are not starving a state, you are guaranteed to converge. So you can just define any kinds of algorithms. Okay.
Question.
Yes.
So what happens after these replacements? Does the optimality go away, or?
What happens to optimality? Yeah, so find and revise always says that as long as you're not starving any state in the find step, you are guaranteed to converge. And so it's guaranteed to converge, and it's guaranteed to converge to optimal for those subset of states. Okay, so
as long as your costs are positive.
As long
negative.
as your costs are
non-negative.
positive. That is correct. The same A star assumption. That's right. Thank you. I have to check. As long as the value function is admissible, it may actually work for the general SSP setting as well. Maybe it actually does work for the general SSP setting. Okay, so I am around 5 o'clock mark. So there is another algorithm called real-time dynamic programming, which is pretty interesting, which explores the states more randomly, but I'm actually not going to get too much into the detail of it. This was an algorithm that Barto and Satinder Singh and so on, they came up with, and they are sort of doing trials. So in a trial, they're just randomly sampling and doing backups only on the set of states that you are sampling. That's actually a pretty cool algorithm, except that they did not have a convergence criteria. They just said that you keep doing this for infinite time and you're guaranteed to converge. And then later when the planning guys looked at it, they defined a termination test on it, which is the labeling test, which is sort of sending information back from goals, saying that if I am very close to the goal and my value function is getting converged, then I can label this state solved, and then I can transfer this information back, and when my start state is solved, then the whole process is solved. I'm not going to get into it in the interest of time, and I will actually skip the details, but the main point is that by using the explicit knowledge of goals, I can actually create a good termination condition for RTDP, and there are a set of algorithms again, because it's again an instantiation of find and revise. It also has some very nice properties, that it's an anytime algorithm, because it focuses its attention on more probable states early on, and so you start to have a very good policy very quickly, and then you are slowly converging to all this to optimal values. And there were some extensions that were proposed, which we won't get into. So the last thing that I want to quickly bring up is, where do heuristics come from? We have sort of, yes.
What about the optimality in RTDP you are saying?
Again, in LRTDP, as long as you are starting with the admissible heuristic function, and you are not starving any states, with LRTDP will not, because it's randomly sampling the outcomes, it will always converge to the optimal. And that's true for all find and revise algorithms, because as soon as you start to see them in the context of find and revise, then that theorem applies, and it's works. And usually, where do heuristics come from? So again, there are some domain-dependent heuristics that you can use, but as I said, we don't want to use domain-specific information. So people write these domains in some representation, and we use the properties of that representation to compute domain-independent heuristics. That's part of the classical planning literature also, and that's part of the probabilistic planning literature also. And again, we're not getting into it. So the main take-home that I would like you to take from this discussion is that when the start state is given to you, you can do much better than going over all states. And there, the main idea is this alternating algorithm, where you focus your attention on the subset of states that you think you can reach right now with the best policy. You recompute the best policy using some well-known updates, and then you recompute the set of the states that you should be looking at, and you keep going back and forth into it, and whenever both of them converge together, then you have actually converged the problem to an optimal solution, assuming you have an admissible heuristic, and to a suboptimal solution if you have inadmissible heuristics. So it's not saying that you can't start with inadmissible heuristics. You can, and in practice people do. Nobody starts with admissible heuristics for really large problems, because they are guaranteed optimality, never going to converge. So you start with less not admissible but more informative heuristics, and that give you suboptimal solutions, but often much faster. Okay, and just before we move on to some of Andre's work, just a shameless plug, if some of this is beginning to interest you, Andre and I worked very hard on writing this synthesis lecture, which has a lot of various algorithms that the planning community has worked on, and we have also adapted the UCT stuff in it, and how to compute heuristics automatically. Can I use ADDs, algebraic decision diagrams? How can I use a basis function representation? How can I use hierarchies? How can I hybridize multiple kinds of algorithms, and so on? How can I partition state spaces into a set of partitions? What happens in external memory? A lot of stuff is actually in it. You're welcome to have a look at it. Okay. So changing gears, yes, Shiva.
I just wonder if you can give us an example which shows us these savings by just looking at a part of the state space, the kind of problems where this would apply. And
there are a ton of them. Basically, I have not seen any problem where value iteration or policy iteration beats LA or star or LRTDP. For all the planning, so we have this idea of international probabilistic planning competitions, and in we have really, really large problems, 15 blocks, they can explode, and you have to come and have them in a specific configuration, or you are driving and the tire gets burst, or lots of elevators problems, and lots of these problems, they all have really large state spaces. You basically never try to do value iteration, because you can't, usually you can't even enumerate the whole state space, so there's just no point starting to try to do value iteration. But even for smaller problems, there may be some problems where the connectivity of the graphs is extremely high, like we had a question there. So if the branching factor is super high, getting to the order of n, maybe value iteration is better, but unless, except for those cases, actually it's assumed that heuristic search is going to be much faster. Okay, so let's see how far I'm able to reach, but I'll hopefully try to give you the high level ideas in both of these. So the first thing that I'm going to start from is the problem of automatic basis function discovery. And now you may not get the context here, but there was some planning research where they came up with these really cool MDP algorithms, and then they put it up in a competition, and what happened was that none of the MDP solvers actually won. What won was a really dumb algorithm which was doing classical planning. I won't call it a dumb algorithm, it was actually it was one of the fastest classical planners at that time, but it was dumb in that it was not even using probabilities. It was just saying, ooh, probabilities, let's get rid of them, and let's determinize the domain in not even clever ways and just do replanning if it fails, but just try to follow the classical plan. So that really became very controversial in the mid 2000s, and so there's a huge stream of literature that came out which starts from the idea of determinization of the probabilistic domain and uses that for efficient planning. So there was this determinization world which exploited the fact that classical planners are really fast, but they were troubled by interesting contingencies like interesting probabilities and so on and so forth. On the other hand, there is this awesome work in reinforcement learning which is talking about function approximation, right? You do dimensionality reduction, you represent state values with basis functions. We thought, but you needed a human to get to those basis functions. So we thought that maybe, just maybe, we can use the idea of determinization to automatically compute these basis functions and then use the dimensionality reduction ideas that already exist, and we'll get we will be able to expose problem-specific structure in a fast, problem-independent way. And so that's the mindset that we started working on. And so the first, so in order to explain this, I'm actually going to use a toy example. So you have a gremlin and an aeroplane, and gremlin, as gremlins are, he wants to sabotage the aeroplane, right? So this is how life is. So basically he wants to stay alive and wants to break the plane. That's my goal. And he can do it using 5 actions. It can get this screwdriver, it can get the wrench, or it can get the hammer. If it has a screwdriver and a wrench, it can try to tweak the plane and cause it to burst. On the other hand, if it has a hammer, it can just bang the aeroplane, and then with a high probability the aeroplane will be burst, but with some probability the fuel tank may explode and the gremlin may die itself. Okay, so that's our toy example. You can figure out what you would do if you were the gremlin. And so this is really an SSPS0 MDP. So my state of states, now this is how you start to think about these problems. My state of states is 32, but you don't write them as 32 states, you write them as 5 state variables. Is gremlin alive or dead? Is aeroplane good or burst? Does it have the screwdriver or not? Does it have the wrench or not? So you have 5 state variables, all Boolean, 32 states. Set of actions are get hammer, get screwdriver, tweak, smash. You have a transition model, you have some action costs. You have a start state which is of the form, again, gremlin is alive, the plane is good, it doesn't have a tool, and your set of goal is represented again compactly by the representation that the gremlin should remain alive and the aeroplane should be burst. So notice that 32 states, 5 actions can be compressed in a very small space when using these factored representations. So I'm going to talk about retrace. Again, this work has a bunch of contributions, but I'm going to talk about a retrace, which is a scalable approximate MDP solver, which combines function approximation with classical planning. It uses the classical planner to automatically generate these basis functions, and it's a fast, memory efficient, and high quality policies are returned. So this is the block diagram. We use LRTDP, but you can use any state space exploration routine. Now, the first thing we would do is that we would determinize the domain, and I'll explain each of these very soon. So we'll determinize the domain and we will run a classical planner. This classical planner is essentially a trajectory, right? It's a single trajectory to the goal. We will compute basis functions from this trajectory, and these basis functions will go into the value computation component, and so that given a new state, we can use this value computation based on this basis function and send the value out. And then there will be a second part of the puzzle that we will talk about a little later. So let's talk about determinization. So what is the idea of determinization? If I have an action that leads to two states with different probabilities, converted into two actions which lead to exactly one state each with probability 1 or deterministic actions. So for example, if I have the gremlin, plane and hammer in my hand, then I can, what was the action? Smash. And with probability 9/10 this happens, with probability 1/10 this happens. I'm going to convert this smash into two actions, smash 1 and smash 2. Both will have the same precondition, but they will have different effects. In this case, exactly this is going to happen. In this case, the gremlin is going to die. Okay. Now this seems silly. The reason it is silly is that now there is no connection between this effect and this effect. We have lost the information that single action is going to lead to one bad or one good outcome. We have converted into two actions, both in our control. So that's actually going to hurt the classical planner significantly, but then we'll recover from it very soon. So you run the classical planner, that's the easy part. So you ran the classical planner, what will the planner do? It will say you can pick up the hammer and then you can use the smash 1 action. This is what the classical planner might return. It may return the other trajectory also. Okay, and it has no idea that there is a bad outcome hanging around here. Now, we convert this into basis functions. Okay, so now you have to start thinking about what's the idea of a basis function. In a very general MDP, I mean it could be gremlin, it could be logistics, it could be blocks world. What would a general basis function mean or may mean? What could one potential definition be? So, this is what we are going to do. So, this is the exact path that was followed. We will go backwards from the goal. So, initially, we have the goal, which is gremlin is alive and the plane is burst. You can regress the smash 1 action, and that leads you to the configuration that in order to actually use the smash action, what should have happened? Gremlin should have been alive, the plane should have been in good condition, and it should have had the hammer in hand. And for regressing this action, what are the weakest conditions that you need in order to execute this action? Gremlin should be alive, the plane should be good, and there should not be any hammer in the hand. So essentially these were states. These on the other hand are just, they are partial states. These are sets of states actually. These are conjunction of literals or conjunction of state variables. Essentially what this is saying is that whenever gremlin is alive and aeroplane is in good condition and it does not have the hammer in hand, it can execute this two-step trajectory and get to the goal in the deterministic world. So these sort of become like my basis functions. They allow me to go towards the goal. They are those structures in the state that allow a certain trajectory to the goal to be allowed, right? We can prove actually that if such a thing is true in a state, then I can run this trajectory and get to the goal. Right. So in other words, I have a non-zero probability path to the goal if something like this is true in any state. And so these become my basis functions, and I can also assign them initial weights based on the cost of these actions. Question?
So something seems very strange here. When you determinize, all the probability information is ignored by the planner, right?
Yes.
So it might decide to choose an action just because it sees a higher reward upstream, whereas
Yes.
the probability of actually going on that path might be extremely small.
Exactly.
Expected reward might
and
be
so
very small.
further computation, when we are learning the basis function weights, is going to account for it. So this is the discovery of the structure of the domain that allows me to go towards goal. Which basis function is good, which basis function is bad, will be learned when we do parameter optimization, when we do value iteration or RDDP and so on. Shiva.
Will you ever discard basis functions and choose new ones?
In our algorithm, we did not discard basis functions, but we incrementally kept adding them.
Right, it might just be that you can get much better basis functions down, like farther down, right?
Yes.
Which have like higher probability trajectories.
Right. So it's also, you have to ask how we use the basis functions. Usually we use sum of basis function representation. In this particular case, we found min to be working better. So we actually used value of action, value of a state is min over all the basis functions. And therefore, if there's a bad basis function, that actually it doesn't matter. It's hanging around.
So by basis function, you mean, be the, so there will be 32 states, right? So, like
So value of a state would be a combination of the basis functions that hold in that particular state. So notice that this particular thing holds in 8 or 4 of the states.
Okay.
Right? Because there are 3 of them are defined, 2 variables are not defined.
Okay.
So this holds in 4 states. So the value of those 4 states will be dependent on value of this basis function and any other basis functions that are present in that state. Any other questions? Okay. So notice that there is one very nice property about these basis functions, that they guarantee that the goal is reachable from this state. There is always a non-zero probability trajectory to the goal. Good or bad, we'll figure out in computation. So essentially now we want to solve this kind of an MDP, which is in basis function, right, taken many MDPs. And now we want to solve, you have to somehow give the probabilistic outcome some meaning in the value function representation. So somehow you want to say that the blue basis function is a better basis function, and this pink, I don't know, it doesn't look like pink, but this other yellow basis function is not a very good basis function, because with some probability it is going to die, and here you are never going to die and you are actually going to get to the goal. And so this happens when you are doing RTDP, and as you are going through these trials and you are doing value updates, you are changing the weights of these basis functions appropriately, and so slowly, because they are using the probabilistic information, this basis function will become much higher cost, and this basis function will stay lower cost. So this is what we have done so far. Basis function enables at least one trajectory. This is applicable from all relevant states. Trajectory is usually combined to form policies, and then the value of the basis function really has to somehow come up with the quality that of the policy that it is enabling, not just the trajectory, and that you do using RTDP in this case, but you can use some other method to do the approximation. And let me just show you some results. So big picture is that it was much more scalable than value iteration, obviously, as well as RTDP based planners which are not using this idea, and it was also at par or better than the best IPPC algorithms at that time, right? So over time these things have changed. So this is LRTDP with the optimal policy, with the admissible heuristic function, and this is a particular problem called triangle tire. Each x-axis is the problem number, and y-axis is the amount of memory that you are needing. So not time but memory, and most of these things are memory bounded rather than time bounded. So LRTDP optimal just crashes after problem 6. LRTDP FF crashes after problem 8. This is inadmissible heuristic, but again LRTDP. And retrace, which is our method, it stands for regression of trajectories for approximate state evaluation, stays fairly low in its memory footprint. That means it's very highly scalable. In terms of the success rate, it does fairly well. So this is the number of successful trials, and retrace gets 100%, and there are some other algorithms which also get well, which are the competitors from IPPC. And then this is another curve for exploding blocks world. So these are lots of blocks, and blocks can explode and stuff like that. Again, you can choose to be careful as to which blocks explode so that you reach the goal more often than not. So here the black one is retrace, and it is doing much better than the best competitors of the time. And as I promised, the largest problems here are, if you look at the original state space, these are 2 to the power 800 states. So can't expect to solve them optimally for sure. Okay. Now, something should ring a bell, although you guys are probably too busy in listening to me. But notice the y-axis. The y-axis says number of successful trials. That means there were trials in which goals were not even reached. Moreover, the problem that I defined, where gremlin can die with some probability, that is a problem where there is an explicit dead end. Once the gremlin is dead, you cannot reach the goal at all. So I am intuitively, without explicitly saying this, introducing the notion of dead ends in the domain. Whereas if you go back to the original conditions that we had for SSPs, which Chaba also questioned, we said that there should be a proper policy from every state. There should be a path to reach the goal from every state with probability 1. That's not happening. So really we are not solving SSPs here. We are solving problems which are more complicated than SSPs, which are relaxing some of these conditions. And I'm going to come to that very soon. But what are we trying to solve? I'll come to that very soon. But let me talk about one other important thing. In the context of dead ends, retrace actually has a very difficult time. Because what happens is that you give a state to a classical planner. The classical planner goes on forever, can't come up with a plan. At some point you say, this is a dead end. I'm just going to store it as dead end. But there are too many dead ends to store. And if you keep adding this actually is a huge sink on the time and on the memory. So we said that as we created good basis functions, these were the basis functions that would lead to the goal with high probability. Can we create bad basis functions? These would be compact representations of substructures which will guarantee that you cannot reach the goal anymore. And to do this, we had to come up with an algorithm which would identify, which will be fast enough, and it will be able to lead to quick dead end discovery. So unfortunately, the joke is lost, and the joke was, yes, we can. We have to come up with feature combinations whose presence guarantees that a state has to be dead end. So in this particular case, and so if you looked at the classical planning world or the SAT world, think no goods in your mind. So in no good, you know that if that is true, then the problem is not solvable, or something, or that assignment is not solvable. In this case, the no good is that if that is true in a state, then I can't reach the goal, come what may. And what's a good representation of no good here? Gremlin is dead. Sorry? Right, not possible together is a fair thing. I'm trying to even come to something very, very simple. What is something very common in all these bad states? Gremlin is dead, exactly. So one very compact way of saying that some state is a bad state is that we don't want gremlin to be dead, basically we want gremlin to be alive. This is a compact representation. Once I know this, I have proven 16 states to be dead ends right there. Right? But if I don't know this, I have to enumerate all 16 of them and keep adding them in my list. So how do I do this? So we have a generate and test procedure for it. We will not get into the details, where we try to construct a potential no-good by sampling, sort of machine learning-ish, and then we ask a sound procedure to verify it for us, whether it really is a no-good. So I'm going to skip this. Except to say that some problems become solvable because of this algorithm, which we call sixth sense, and it's the amount of savings that it gives in memory and time is huge. Okay, so let me finish the third part of the discussion around this point. So the main take home is that you want to learn the structure of the domain completely automatically from the representation that is given to you. And in this particular case, we learn that by regressing the trajectories in a determinization world, which would represent some good structure, and in this case the good structure is that they guarantee a non-zero probability path to the goal. And similarly, we represent bad structure where you say that if this structure is true in a state, then goal is absolutely not reachable. So for all these states, the value is obviously infinity. For the states which have basis functions present in them, that means there is some path to the goal. You have to learn the weights of those basis functions, and then you can do that using some kind of an exploration procedure, an optimization procedure. So this allows, this was at the time a very novel use of classical planners for MDP algorithms, because it retained the decision theoretic nature of what are the various outcomes that are happening of an action, but it also exploited the scalability of classical planners. And from RL side of things, it's one of the automatic ways to generate basis functions by using this symbolic analysis technique. And a key take-home message pops up that factored representations can really expose useful structure. Okay, so let's see, I must have 5-7 minutes, 4. So I'll try my best to complete this in maybe 5 or 10 minutes. Basically, and here's a little chuckle, as I see it from my vantage point, this workshop has been about generalizations and unifications. Value functions get generalized to generalized value functions, gradients get generalized to extra gradients. Well, I want to stand in this elite audience and say, yes, I can generalize something as well. So I'm going to be generalizing SSPs. And this is sort of exactly the question that Abba asked a little while ago. Do I need these two restrictions? Okay. Going to be a little fast, but the main point here is that a proper policy from all states is too restrictive. It absolutely disallows dead ends, but we need dead ends in the domains. And moreover, you also allow that an improper policy incurs a cost of infinity from every state, and this allows, and this is important because if this doesn't happen, then algorithms won't halt. And if dead ends happen, then it's going to be very complicated. So first of all, I'm going to argue that dead ends are important. In any domain you can think of, there will be dead ends. The rover can fall into a ditch and never recover. If you're trying to climb Mount Everest, then you can die. And if you're trying to just meet a deadline, there is some probability that you may never meet that deadline. It just can not happen. It will, with small probability, these things will happen. So if I have a model that completely gets rid of dead ends, then that's not a very practical model. So in that sense, we started asking the question, well, what is the space of goal-oriented MDPs? We defined stochastic shortest path, and let us suppose this is all the well-formed goal-oriented MDPs, what is in the middle, right? And we like stochastic shortest path because they lead us to these efficient heuristic search algorithms and so on and so forth, but what is here? And how can we solve them efficiently? Okay, so we defined a series of models. I'll talk just briefly about two of them. One very easy one, which is what we call SSPADE, which stands for stochastic shortest path with avoidable dead ends. There are dead ends, but I have a start state, I can avoid them, right? There is a ditch there, I'm not even going to go close to it. I'm just going to stay far away, not even tread that thin line. And you can do this, and the problem is that you can't compute V star of S for every state, so value iteration is not even applicable in this particular setting because it diverges. But we only need the relevant states to get the right value, so you can use heuristic search and solve them. So that's the good news. Okay. Now there are some conditions as to when that happens. Sometimes the dead ends can't be avoided, so we also have a series of models which are called SSPs with unavoidable dead ends. We basically decided to add penalty on them. The penalty can be finite, then it's called FSPUTE, and the penalty can be infinite, then it's called ISPUTE. ISPUTE is much harder than FSPUTE, but I'm not going to worry about it. Now I'm going to talk about one other algorithm, one other model that I think is pretty cool. It is cool because it's very unintuitive. So this is sort of the interesting, maybe next 3-4 minutes are interesting. So suppose I am only interested in maximizing the probability to reach the goal. Okay, so costs don't matter. Moreover, we can set them to 0. You can think of them as rewards if you want to. So most rewards are 0 except the reward that takes me to the goal state. That reward is 1. Now, the beauty is that value iteration is not going to converge, even though there is a well-formed value function. So what is the probability to reach the goal from any state? It's a number between 0 and 1. It's either 1 if I can always reach it, it's 0 if it's a dead end, and it's somewhere in the middle if with some probability I reach a dead end, and it's some probability I reach the goal. So the value function is bounded. In fact, it's bounded between 0 and 1, but value iteration is not going to converge. And even if it did converge, you may not find the optimal value function. So let's look at some examples. So this is an SSP, because I can always reach the goal, and each improper policy has an infinite cost, okay, or minus infinite reward. These, on the other hand, are not SSPs. For example, here there is a zero cost cycle. Now, when you have a zero cost cycle, right, you can just keep doing this looping within your current policy, and the value of the policy will not become infinite. So it's not an SSP. So, but this is the kinds of things that happen in MaxProb, where we are trying to maximize the probability to reach the goal. So we decided to explore this further, and we came up with a generalization of SSPs, which says the following. So it's a reward-oriented MDP. So we are maximizing. We say that we have a constraint that we want to reach the policy, we want to reach the goal with probability 1. Moreover, we relax the other assumption that sum of rewards costs is infinite, or sum of rewards is minus infinite. Now we say that sum of non-negative rewards accumulated by any policy starting from S0 is bounded at above, bounded from above. Now, it's a technical definition, but you can prove that MaxProb is actually a subset of generalized SSPs. So let me take this example. Main point what GSSPs does is that it allows these kinds of structures where you have zero cost cycles, but it does not allow these kind of structures because sum of non-negative rewards in this particular loop is going to diverge. So that's not going to allow, that's not going to help, but this one is all right. Okay. So let me show you some really counterintuitive properties of this generalized SSPs. The first thing I will show the good property, that in this case there is a proper policy, right? What is the proper policy? From S0 go here, from S3 go here, and from S4 go to the goal. So this is a very well formed GSSP. For any policy, sum of non-negative rewards is always less than equal to 2. So that means sum of non-negative rewards is always bounded from above. Why? Because either I will take this action 2 and then go inside the loop, or I will take this and then go inside this loop, or I will take this and go to the goal. Either of those cases, at least my reward is at most 2, so I am bounded. So it is technically satisfying those properties. And this is exactly the solution that we are looking for. And this is a bad solution, right? So this one is looping, it's not reaching the goal, it's a bad solution. So we are looking for this and we want to avoid this. What's the big deal? Let's do value iteration. Okay, so some interesting things. First of all, you have this Bellman backup operator. So if I ran value iteration starting from V star, would I get V star? Actually, I would get V star, right? So what's the optimal value function? This is 0, this is minus 1, this is minus 1, and this is minus 1 plus 0.5, which is minus 0.5. So this is actually a fixed point of GSSPs. That's good. So Bellman operator is still working, is it? Well, actually not. The problem is that it is not a unique fixed point of the Bellman operator. So there are many value functions which are fixed points for this particular kind of a DB. A case in point, this is the optimal, but this is a fixed point. Why? Because V of this is 1 and this is 1 plus 0, so 1, so it's fine. Here I am going to the goal, so it's minus 1 plus 0 versus 1 plus 0, 1 is max, so 1 is the value. So this is a fixed point here, this is a fixed point here, but this is not the optimal fixed point. This is not what we are looking for, because this is not going to give us the right policy, because here it will say you should take action 2 and go there. Secondly, moreover, all suboptimal fixed points are actually no, this is wrong. Oh, actually admissible. That's right. This is right. So all suboptimal fixed points are admissible. If you're starting from an exactly inadmissible value function, then there are no fixed points. But in admissibility, there are fixed points. Even more problem, even if you stopped with V star, if you just did greedy and picked any policy at random from the greedy, you may not get the optimal policy. For example, this is the optimal value function, but here you may just pick the, from here you may actually pick going to this state as your optimal policy.
Sir,
Yes.
sir, I don't get this -2. Why did you fix this minus?
Where did I fix -2? Oh, I just said that it should be bounded from above. In this particular case, it is bounded from 2, but it should be bounded with any value. It's a technical constraint that you need for the algorithms to work. So therefore, heuristic search does not work, and the reason it does not work is that it sort of fall into traps. Basically, it gets into these value functions which are not optimal, and this happens because of these zero cost cycles. So essentially, to get this to work, and I'm skipping over a lot of information, we had to define this general framework. From find and revise, we had to define the idea of find, revise, eliminate traps. The idea being, find a state where the value function has not converged, do a value iteration, but now you may be in a suboptimal place. So if you are in a suboptimal place, you try to eliminate traps. So let me show you with an example. So suppose I start with this value function. I do f and r till convergence. So I get this value function. This is a bad value function because it's not optimal, and the reason it's not optimal is because there is in the greedy policy there is this infinite loop there, infinite zero cost loop. So you eliminate this, you set it to a different value, rerun find and revise. Maybe you get this value function. Again, this is not optimal because the greedy policy has this particular zero cost loop in it. You again find it, you remove it, you convert it into a meta state and give it a value function. Again you run it, and finally you will converge. So this is the general idea. So V star is a unique fixed point of this fret operator that we had to define, which did find, revise, eliminate traps, and this allows us to solve these problems. Let me show you some results. So this is again another case in point where value iteration will not scale, but heuristic search may do much better. This is of course on much smaller problems because it's a harder problem.
Question.
Yes.
So by trap, basically you're searching for cycles with where
Zero costs, all cost zero.
is it all cost zero or all non-negative costs zero? I mean, negative, completely negative cycles are also
So
trapped, right?
completely negative cycles
No.
will not be bounded. So you want all policies to be bounded from above. That condition eliminates all negative cycles. Right. Okay, so let me basically stop around here. So what we did is that we thought that there is discounted reward MDPs, there are finite horizon MDPs, and there is a class SSPs, which is a really good class, and it is a really good class. But then there are classes that go beyond it. So if you have finite penalty on dead end, then it's actually SSP. But then we talked about avoidable dead ends, and it's an extension of SSPs, very good extension of SSPs actually. And then there is a max drop problem that we talked about, and then there is the generalized stochastic shortest path problem, which had these general definitions of non-negative boundedness, and max drop is a subset of it, but so are some other well-known problems. So Putterman's book talks about positive bounded MDPs and negative MDPs, and there are special cases of GSSPs. Then there is another class called infinite penalty stochastic shortest path, which is actually even which has non-zero intersection. And then the question that people have been asking is that what's the most general model in goal-oriented MDPs, which is well formed. There is an optimal policy that we can look for, and that somebody called stochastic safest and shortest paths, S3Ps. This is work in France, and they try to relax to as many kinds of costs as possible. They are unavoidable dead ends. There are alternating cost cycles, zero cost, and there are even negative non-positive cycles as long as they don't need to be taken to reach the goal. And you can actually prove that the stochastic longest path problem, it can be reduced to stochastic longest path. No, stochastic longest path can be reduced to S3Ps. So this is actually an NP hard problem. So MDPs is a polynomial problem in state space. S3Ps is actually an NP hard problem in state space. So not much work has been done on this particular area, but anyway. Okay, so I'm basically done. and I'm quite late. So SSP MDPs exclude interesting planning scenarios, and we can generalize them to generalized SSPs, which can handle a lot of interesting properties. A lot of well-known MDPs are subclasses of these, and we can even have a heuristic search algorithm for this kind of a model. Okay, so let me stop here. I have not been working on this sort of stuff anymore, but Ankit, who's here, has been looking at abstractions, and in particular, we have been pushing work of Ravindran and earlier work by Given, where Given used to do state abstractions, Ravindran did state abstractions with action mapping, and we have been working on state action pair abstractions. Unfortunately, don't have the time to talk about it, but it's a strict generalization, and we get really good empirical results. So I'll end here. These are three messages. Search is good, representation is good, and goals allow you to give additional structure that you can exploit. Thank you. Or in the next hour. Or in the next hour as well.
No, I probably want to get back to your guest house plan.
Yeah, but yeah, I'll be missing the rest of the workshop, but this is a great workshop, and I'm really, really happy that.
You're taking things, we'll put them on YouTube.
Thank you.
So I have a question.
Yes.
Great talk. One thing you didn't mention, and I thought maybe we should bring this up. In the context of classical planning, people sometimes talk about the need or desire to avoid ever representing the state. And what they mean by that typically is that the state is a very concrete object, right? It's sort of like the full unrolled representation, if you will, and you somehow never want to do that. You sort of want to keep, you want to keep your representation compact, so you never really have to worry about dealing with the actual state of the world. Is that something you see in this literature?
Not very often. So my understanding is that so the main they have seen three ways in which people represent the search space in classical planning. Actually, four ways. One is standard state space search. One is backward search, where they are representing subsets of states using regression, goal regression, and sub-goals. One is what is called partial order planning.
Right.
And one is often they do local search in the full plan space. Now, to my best understanding, the best planners are not regression planners and are not partial order planners, more often than not. In fact, the modern work is using the idea of landmarks and so on and so forth. And to do that, they are working mostly in the forward state space search and sometimes in plan space when they're doing local search. So traditionally, if you go back to 90s and so on and so forth, there was a lot of work on partial order planning and some work on regression planning. But the current state of the art usually does heuristic search, very interesting heuristics, very carefully constructed heuristics in the forward direction. So the state is explicitly maintained. That is my best understanding. There is some work on first order MDPs and so on and so forth where people do use basis functions, but that work hasn't really come mainstream so far.
Awesome.
Yes.
So your work is all on planning, and that's all very nice. But let me ask you to step outside your normal
Sure.
thing for a moment and ask about what if, in the long run, eventually the models are not going to be provided to us. We want to be able to get models from learning processes, and so that's going to be very challenging because the interaction. What are the what do you think about this problem of how we are going to ultimately need to acquire the models from experience, I guess.
Right. So I think that's a fair question, and more often than not, you find people providing the structure but not providing the probabilities. So that becomes like a relatively easy problem, but you can learn the probabilities using some idea of reinforcement learning. There is some work on learning strip style operators from data. So there is work on converting the learning problem in the factored representation itself. There's also some work on, and this is my other hat, so some of my work is in planning, a lot of my work is in language these days. There is some fascinating work on reading text and converting it into strip style action representations, where you can figure out the preconditions and effects from text itself. I think in the long run, a combination of all these things will come together. I don't have a very carefully thought out and very deep answer to it. I am by in no way saying that reinforcement learning is not necessary. In some of my work in crowdsourcing, which I'm doing a lot of, where planning does show up, we do just, so the complication is not that much there. So we often do greedy reinforcement learning and estimate the model. So we do model-based reinforcement learning using epsilon greedy, and it gives us much better results than not doing it. But maybe a more interesting reinforcement learning algorithm might be handy. But yeah. Cool, thanks.